Jupiter has flung thousands of objects out of our solar system. That's its job, the protector, the shield. But here's what nobody mentions. For every object it throws away, it aims another one inward. Right now, an interstellar visitor called 3I Atlas is approaching the gas giant at over 60 kilometers per second. And something strange is happening. The trajectory isn't behaving. Small forces nobody fully understands are nudging it during the most gravitationally intense moment possible. If those forces align just right, Jupiter doesn't deflect 3I Atlas away from Earth. It points it directly at us. What if these small forces we barely understand are turning this visitor around, using Jupiter's gravity as a pivot point? Stay until the end, because the answer determines whether we're witnessing a close call or the beginning of something we cannot stop. If you're as captivated by this cosmic mystery as I am, go ahead and like this video and subscribe so you stay connected as new information emerges. Leave a comment telling me where you're watching from, what hour it is in your corner of the world, and what you think is really happening out there beyond Jupiter's orbit. Part 1. The claim nobody wants to touch. Jupiter has always been our protector. That's the story we tell ourselves. The solar system's largest planet, a gas giant with gravity so intense it bends light, stands between us and the chaos beyond. For decades, astronomers have described Jupiter as Earth's bodyguard, a cosmic bouncer that catches or deflects asteroids and comets before they can reach the inner planets. We've built an entire reassuring narrative around this idea. Jupiter shields us. Jupiter saves us. But what if that's only half the story? What if, under the right circumstances, Jupiter doesn't protect Earth at all? What if it aims? On October 7th, 2023, astronomers confirmed something extraordinary. An object designated 3I Atlas became the third verified interstellar visitor to our solar system. Not from the Kuiper Belt, not from the Oort cloud, from another star system entirely. It came screaming through space at velocities no natural solar system object could achieve, carrying with it the mystery of whatever stellar neighbourhood birthed it. By all conventional understanding, 3I Atlas should behave exactly like its predecessors, Oumuamua and 2I Borisov. It should pass through our solar system once, never to return. Interstellar objects don't orbit our sun. They don't belong to our gravitational family. They're tourists, not residents. They come, they go, and we never see them again. Except something strange happened as 3I Atlas approached Jupiter. The trajectory calculations started changing. Not dramatically, not in ways that made headlines, but enough to catch the attention of a handful of specialists who model orbital mechanics for a living. Small refinements in the predicted path, tiny adjustments to the expected exit velocity, the kind of changes that usually mean better data, better instruments, better understanding. But this time, some of those refinements pointed in an uncomfortable direction. They suggested that 3I Atlas might not be leaving as predictably as everyone assumed. Let me be absolutely clear about something. No space agency has issued a statement claiming 3I Atlas is turning around. NASA hasn't called a press conference. The European Space Agency hasn't raised alarms. The official position remains unchanged. This is an interstellar object on a hyperbolic trajectory, passing through, not staying. But in the margins of observational data, in the quiet conversations between researchers who study gravitational interactions, a different conversation is happening. It's speculative, it's uncomfortable, and it centers on a phrase you won't find in any official report: powered slingshot. The concept sounds almost absurd. Slingshots, in the context of space travel, are gravity assists. Spacecraft use them all the time. Voyager used Jupiter's gravity to accelerate toward the outer planets. Cassini used multiple planetary flybys to reach Saturn. These maneuvers are passive. The spacecraft doesn't fire its engines during the close approach. Gravity does all the work. The object comes in fast, whips around the planet, and leaves even faster, redirected but fundamentally unchanged in purpose. A powered slingshot would be something else entirely. It would combine gravitational acceleration with active thrust, using Jupiter's gravity not just as a speed boost, but as a pivot point. A U-turn at cosmic velocities. Why would anyone even consider such a possibility? Because of orbital residuals. That's the technical term for the tiny mismatches between what orbital models predict and what telescopes actually observe. Every calculation involves assumptions. The mass of the object, its shape, its rotation, whether it's venting gas or shedding dust. These parameters get plugged into equations that spit out predicted positions, velocities, trajectories. When the real observations don't quite match, you get residuals. Usually they're small, usually they're explained by better measurements or slightly refined assumptions. Usually they don't matter, but residuals are also where surprises hide. They're the cracks in our confidence. Every major orbital surprise in history, every unexpected trajectory change, started as an unexplained residual. When Oumuamua deviated from its predicted path in 2018, scientists initially dismissed it as observational noise. Then the deviation persisted. Eventually they had to accept that something was pushing it, some force beyond gravity alone. The current consensus blames outgassing, jets of sublimating material acting like tiny rocket engines. Uncomfortable, but explainable, natural. The residuals around 3I Atlas are smaller, more subtle, but they exist, and they're persistent. Some researchers have noted that certain assumptions in the models, particularly regarding the object's mass distribution and rotation state, could be wrong, not wildly wrong, just wrong enough. If the mass is different than estimated, the gravitational interaction with Jupiter changes. If the rotation creates asymmetric outgassing, thrust vectors shift. If the timing of perihelion, the closest approach to Jupiter, coincides with peak activity on the object's surface, effects compound. Here's the fragile assumption underlying every confident prediction about 3I Atlas. We understand all the forces acting on it. Gravity from the Sun, gravity from Jupiter, maybe some outgassing if it's a comet. Add them up, solve the equations, predict the path. Simple. Except it's only simple if the list is complete. If there's even one force we're underestimating, one parameter we've measured incorrectly, one interaction we haven't accounted for, the predictions drift. And at interstellar velocities, even small drifts accumulate into enormous positional changes over time. So why isn't this discussion happening in press releases? Why are official statements still confident that 3I Atlas is leaving forever? Because extraordinary claims require extraordinary evidence, and right now the evidence is circumstantial at best. The residuals could mean a dozen different things. The trajectory refinements could be artifacts of improving data quality. The speculation about powered maneuvers could be exactly that. Speculation, unfounded, and irresponsible. No scientist wants to be the one who cried wolf about an interstellar object. No agency wants to incite panic over uncertainties that will probably resolve into nothing. But here's the question nobody wants to ask out loud. What if the assumption that it's leaving is the mistake? What if we're so invested in the narrative that interstellar objects pass through and disappear that we're missing something right in front of us? What if Jupiter's gravity, that immense protective force we've always celebrated, is about to do something we never modelled for? What if, instead of deflecting 3I Atlas away from Earth, Jupiter is lining up the shot? Part 2. Jupiter, shield, assassin, or neutral party? Jupiter is not your friend. It's not your enemy either. It's a gravitational fact, indifferent and immense, warping space-time around it with the casual authority of something that outweighs everything else in the solar system except the Sun. 417 times the mass of Earth, packed into a sphere so large you could fit over 1,300 Earths inside it. When you talk about Jupiter's gravity, you're talking about a force that shapes not just its own neighbourhood, but influences every trajectory in the inner solar system. And we've told ourselves a very comforting story about what that influence means for us. The story goes like this. Jupiter sits out there in the 5th orbital position, a massive gravitational sink that catches or deflects dangerous objects before they can threaten Earth. Comets coming from the outer reaches, asteroids knocked loose from unstable orbits, they all have to pass through Jupiter's sphere of influence. Some get captured, some get ejected entirely from the solar system, some get redirected into harmless paths. Earth benefits from this, we're told. Jupiter is our cosmic bodyguard, our planetary shield, the reason we haven't been pummeled into sterility by a constant bombardment of deep space debris. It's a nice story. It's also incomplete, because Jupiter doesn't just deflect threats outward, sometimes it deflects them inward. Let's talk about Comet Shoemaker-Levy 9. In July 1994, astronomers watched as a fragmented comet slammed into Jupiter with spectacular violence. 21 distinct impacts over the course of 6 days, each releasing energies equivalent to millions of megatons of TNT. The scars were visible from Earth for months. Here's what most people don't realise about Shoemaker-Levy 9. Jupiter didn't capture it from interstellar space. It didn't heroically intercept something aimed at Earth. Jupiter tore that comet apart with tidal forces, locked it into an unstable orbit, and then collided with it. Jupiter created the threat, then absorbed it. The bodyguard metaphor gets a lot less comforting when you realise the bodyguard occasionally beats people up just to stay sharp. Then there are the Jupiter family comets. These are objects that originated in the outer solar system, but got gravitationally kicked around until they ended up on orbits that pass repeatedly through the inner planets. Jupiter didn't shield us from them, Jupiter delivered them. Every few years, some Jupiter family comet makes a close pass by Earth. Most are small, most miss, but most is not all. The gravitational perturbations that send these comets inward come from the same Jovian gravity we're supposed to be grateful for. Gravity doesn't have preferences. It doesn't choose to protect Earth versus endanger it. Gravity is a geometric consequence of mass warping space-time. If you're a small object approaching Jupiter, what happens to you depends entirely on your angle of approach, your velocity, and the timing of your arrival. Change any of those parameters even slightly, and you get a completely different outcome. An object approaching from one side gets flung out toward interstellar space. An object approaching from a slightly different angle gets redirected toward the Sun, and an object approaching at just the right angle with just the right velocity gets aimed precisely at Earth. NASA understands this. Mission planners who design spacecraft trajectories know that Jupiter's gravity is not a shield, it's a tool. A gravity assist doesn't care about the object's intentions or origins. It cares about vectors, velocities, and the curvature of space-time around massive bodies. When Voyager 2 used Jupiter to reach Uranus and Neptune, it was exploiting the exact same physics that could redirect an asteroid toward Earth. The difference is intention and control. Voyager 2 fired its engines at precisely calculated moments to ensure the right outcome. An uncontrolled object just goes wherever the math sends it. And here's the uncomfortable part. At interstellar speeds, Jupiter's influence becomes even more powerful. Think of it as a gravitational lens, not in the optical sense, but in the trajectory sense. A fast-moving object passing through Jupiter's gravity experiences extreme bending of its path. The faster you're moving, the more energy you have, and the more that energy can be redirected rather than absorbed. A slow object might get captured. A fast object gets whipped around and sent somewhere else. The question is, where? For 3i Atlas, travelling at over 60 kilometers per second relative to the solar system, Jupiter represents an enormous energy reservoir. If the object passes close enough on the right trajectory, Jupiter's gravity can add or subtract velocity in any direction. Approaching from behind, Jupiter relative to its orbit adds energy. Approaching from ahead subtracts it. Approaching at an angle redirects. The exact outcome depends on sub-degree precision in the approach angle, and those angles change based on forces we might not be measuring correctly. So is Jupiter protecting us from 3i Atlas, or aiming it? The answer is neither. Jupiter is doing exactly what a 417 Earth mass ball of hydrogen and helium does, warping space-time in proportion to its mass. If 3i Atlas passes through that warped region, its trajectory changes. Whether that change points the object away from Earth or toward it is purely a function of geometry and velocity. There's no shield. There's no weapon. There's only math, indifferent and precise. But human psychology doesn't like indifference. We like narratives. We like protection. We like the idea that Jupiter stands between us and danger, a benevolent giant keeping watch. The reality is more unsettling. Jupiter amplifies consequences. If an object is already going to miss Earth, Jupiter makes it miss by a wider margin. If an object is already going to threaten Earth, Jupiter can make that threat worse. And if an object is balanced on the knife's edge between threat and safety, Jupiter tips it one way or the other with no regard for which outcome we'd prefer. The question we should be asking isn't whether Jupiter protects Earth. The question is, which side of that knife's edge is 3i Atlas on right now? And who's holding the knife? Part 3. Hyperbolic. Until it isn't. Hyperbolic trajectory. The term gets thrown around in astronomy like it's a synonym for unstoppable, permanent, guaranteed to leave. When an object is on a hyperbolic trajectory, it means its velocity exceeds the escape velocity from the solar system. It's moving too fast to be captured. It came from somewhere else, it's passing through, and it's going to keep going forever. The math is clean. The conclusions are definitive, except the math is only as definitive as the measurements that feed it, and measurements are never perfect. Let's start with what hyperbolic actually means in everyday language. Imagine throwing a ball straight up from Earth's surface. If you throw it slowly, it goes up and comes back down. Elliptical trajectory. Throw it faster, and it goes higher before returning. Throw it at exactly 11.2 kilometers per second, and it never comes back. It escapes Earth's gravity. That's escape velocity. Throw it even faster, and the trajectory becomes hyperbolic. The ball doesn't just escape, it escapes with energy left over. For 3i Atlas, the excess velocity is enormous. It's not barely escaping the solar system. It's racing away with enough kinetic energy to make gravitational recapture seem impossible. The sun's gravity pulls on it, slowing it down slightly but not enough to stop it. Jupiter's gravity tugs at it during the flyby, altering direction, but not fundamentally changing its status as an unbound object. By every standard calculation, 3i Atlas should leave the solar system and never return. Should. But hyperbolic doesn't mean immune to change. It means the current velocity exceeds the threshold for escape. If that velocity decreases even slightly, the trajectory shifts. Not dramatically, not in a way that makes the object stop and reverse course like a car hitting the brakes, but subtly. The curve bends a little more, the exit angle changes by fractions of a degree, the excess velocity shrinks, and in orbital mechanics, small changes have enormous downstream effects. How do you measure excess velocity? You track the object's position over time, measure how fast it's moving, calculate how much gravitational potential energy it has based on its distance from the sun, and subtract the two. What's left over is the excess kinetic energy, the surplus that allows it to escape. If your position measurements are off by even a few kilometers, the calculated velocity changes. If your estimate of the object's distance is wrong by a tiny percentage, the gravitational potential energy term shifts. Stack enough small errors together, and your confidence in the hyperbolic nature of the trajectory starts to erode. Now add non-gravitational forces. Outgassing from a comet nucleus creates thrust, usually tiny but persistent. Solar radiation pressure pushes on the object like wind on a sail. Both of these forces can add or remove kinetic energy. If outgassing happens symmetrically, it doesn't change the trajectory much. But if it's directional, if the object is venting gas primarily from one side due to solar heating or internal composition, that asymmetry creates a net force. Over weeks or months, that force accumulates into a measurable velocity change. For a bound object, one that's already in a stable orbit around the Sun, these forces might shift the orbital period by a few days or adjust the perihelion distance slightly. Annoying for precise predictions, but not catastrophic. For an object on the edge of escape, these forces could be the difference between leaving and staying, and we don't measure them directly. We infer them from residuals, from the mismatch between predicted and observed positions. If the residuals are explained incorrectly, the inference is wrong. Here's where things get genuinely uncomfortable. Energy loss in space doesn't look like energy loss on Earth. There's no friction, there's no air resistance. An object doesn't slow down smoothly and stop. Instead, energy gets redistributed between kinetic and potential forms. If 3i Atlas loses velocity during its close approach to Jupiter, that lost kinetic energy gets transferred somewhere, either to Jupiter's orbital motion or to some internal process within the object itself. The trajectory doesn't become circular, it becomes less hyperbolic. The curve bends more sharply. What would astronomers see if this happened? Probably nothing dramatic. Position measurements would continue matching predictions within the error bars. Velocity calculations would stay within expected ranges. The object would still be classified as unbound. But the margin of confidence would shrink. The excess velocity would drop from, say, 20 kilometers per second to 18 kilometers per second. Still hyperbolic, still escaping, just less comfortably so. And then time passes. The object moves farther from the Sun. Gravitational influence weakens, but non-gravitational forces continue. Solar pressure decreases with distance, but outgassing might not if the object has volatiles that sublimate at a wide range of temperatures. The trajectory keeps adjusting, the curve keeps bending, and at some point, if enough energy has been lost, the hyperbolic trajectory becomes parabolic. Zero excess velocity, balanced exactly on the edge between escape and capture, From parabolic to elliptical is a whisper. One more small force, one more velocity change, and the object is bound, not to a circular orbit, not to a stable, predictable path, but to an eccentric, chaotic orbit that swings it back into the inner solar system eventually. Maybe in decades, maybe in centuries. The timeline depends on how much energy was lost and where in the orbit that loss occurred. No such reversal has been confirmed for 3I Atlas. The official trajectory remains hyperbolic. The excess velocity, while smaller than initially calculated, is still positive. The object is still classified as leaving forever, but the word "still" is doing a lot of work in that sentence. It implies ongoing verification, continuous measurement, updated calculations. It implies that astronomers are watching closely, checking and rechecking, making sure the hyperbolic classification remains justified. And if they stop watching, if 3I Atlas moves too far away to track reliably, if the telescopes turn to other objects, other priorities, other crises, then the last confirmed trajectory becomes the assumed trajectory. Hyperbolic because it was hyperbolic last time we checked. Leaving because it was leaving when we stopped looking. Until, decades from now, someone happens to point a telescope at the right patch of sky and find something incoming that looks suspiciously familiar. Hyperbolic until it isn't. The phrase sounds like a contradiction, but in orbital mechanics it's just a description of measurement limits and the gradual erosion of certainty over time. Part 4. The slingshot. Nobody modelled for. Gravity assists are supposed to be simple. You model the object as a point mass with a known velocity. You model the planet as a much larger point mass with a known gravitational field. You calculate the trajectory through that field using equations that Newton figured out 300 years ago. The object comes in on one path, gets deflected by gravity, and leaves on a different path. No engines, no thrust, no complications. Just elegant, predictable physics. Except comets aren't point masses. They're dirty snowballs with irregular shapes, variable compositions, and surfaces that respond to solar heating by venting gas. Asteroids can have similar issues if they contain ice or volatile compounds. And interstellar objects, we've observed exactly 3 of them, which means our understanding of how they behave is based on a sample size that wouldn't pass peer review in any other field of science. We assume they follow the same rules as solar system objects. We assume outgassing, if it occurs, follows predictable patterns. We assume rotation averages out asymmetries. We assume a lot. Non-gravitational forces are real. They're documented. They're measurable. When Halley's Comet returns every 76 years, its arrival time drifts slightly from pure gravitational predictions because outgassing creates thrust that either speeds it up or slows it down depending on the comet's orientation. Comet Encke loses about 2.5 hours per orbit due to similar effects. These aren't rounding errors. These are forces large enough to shift orbital periods by hours or days over the course of a single pass through the inner solar system. Now scale that up to an interstellar object moving at 60 plus kilometers per second. The gravitational interaction with Jupiter happens over a period of days or weeks, depending on how close the approach is. During that time, if 3I Atlas is venting gas, the direction and magnitude of that venting matters enormously. If the object is venting away from the Sun, symmetric and predictable, the effect might cancel out. But if it's venting asymmetrically, if one hemisphere is more active than the other, that creates a net force. A small force, measured in fractions of a millimetre per second squared, but persistent. Here's where the speculation gets uncomfortable. A powered slingshot isn't just about outgassing. It's about timing and orientation. If an object is venting in a specific direction, and that direction happens to align with the trajectory change needed to redirect the object back toward the inner solar system, you get a compounding effect. Gravity bends the path. Thrust nudges it further. The combination produces a trajectory change larger than either force would create alone. This isn't science fiction. This is applied physics. Every deep space mission that uses a gravity assist also fires its engines at periapsis, the point of closest approach, because that's where small velocity changes have the biggest impact on the final trajectory. The Cassini mission fired its main engine during its Jupiter flyby to fine-tune its path towards Saturn. The New Horizons probe did the same. It's standard practice for spacecraft because the math works. A tiny delta V, applied at the right moment near a massive body, gets amplified into a large trajectory change. But spacecraft are controlled. Engineers know the spacecraft's mass, orientation, and thrust capability. They program the engine burns to happen at precisely calculated times. 3i Atlas has no engineers. It has no programming. If it's producing thrust, that thrust is the result of physical processes: solar heating, volatile sublimation, internal pressure release. These processes don't care about optimal timing. They happen when conditions trigger them. Except, what if the orientation isn't random? What if 3i Atlas, through rotation or tidal locking or sheer cosmic coincidence, happens to be oriented in a way that produces thrust at the worst possible moment? Or the best possible moment, depending on your perspective. The moment when Jupiter's gravity is bending its path most sharply, when even a small additional nudge redirects the object onto a completely different exit trajectory. To be absolutely clear, there is no evidence of artificial propulsion. No one is suggesting 3i Atlas has rocket engines. No one is claiming it's under intelligent control, but natural processes can produce thrust. Comets do it all the time. And if a comet-like interstellar object happens to vent gas during its closest approach to Jupiter, the physics doesn't care whether that timing is deliberate or accidental. The outcome is the same. Models simplify. They have to. You can't simulate every grain of dust on an object's surface, every temperature gradient, every pressure differential. You approximate. You assume. You model the object as a solid, non-rotating, non-venting mass, and calculate what happens to it in Jupiter's gravity well. If the real object deviates from those assumptions, the predictions drift. And the more extreme the gravitational interaction, the more those drifts matter. Orientation during close approach could matter in another way. If 3i Atlas is elongated, cigar-shaped like Oumuamua, its gravitational interaction with Jupiter depends on which end is pointing where. A long object passing close to a massive body experiences tidal forces, gravitational gradients that pull harder on the near side than the far side. If the object is tumbling, those forces average out. If it's rotation locked, if one end consistently points toward Jupiter during the approach, the tidal coupling becomes asymmetric. That asymmetry could torque the object, changing its rotation state, which in turn affects how outgassing produces thrust. This is the kind of complexity that makes scientists uncomfortable but curious. Uncomfortable because it introduces too many variables, too many unknowns, too many ways for predictions to fail. Curious because nature doesn't care about simplifying assumptions. Nature does what the physics demands, and sometimes the physics is messy. So when someone says 3i Atlas is on a simple gravity assist trajectory, what they mean is, we've modelled it as a simple case, and the observations mostly match. But models are only as good as their assumptions. If any assumption is wrong, if the object is venting, if it's oriented unusually, if it's responding to forces we haven't accounted for, then the simple model is just a comforting fiction. And the real trajectory is something we won't understand until it's too late to matter. Part 5. The silence problem. When an asteroid is discovered, especially one that might pose a threat to Earth, data flows quickly. Observatories track it. Orbital calculations get updated daily. NASA's Center for Near-Earth Object Studies publishes refined predictions. Amateur astronomers chime in with their own observations. The object gets a name, a designation, a risk assessment. The process is transparent, iterative, and public. Within weeks, sometimes days, the scientific community reaches consensus on whether the object is dangerous, and if it's not, everyone moves on. For interstellar objects, the process starts the same way. Initial detection generates excitement. Telescopes around the world swing toward it. Data pours in. Orbital elements get calculated. The object gets classified as interstellar based on its velocity and trajectory. Papers get published. Press releases go out. And then, gradually, the attention fades. Not because the object stopped being interesting. Because it's so far away, moving so fast that tracking becomes difficult and expensive. Telescopes have limited time. Other objects need observation. Priorities shift. This is normal. This is how astronomy works. You can't track every object forever. You gather enough data to characterize the trajectory, confirm it's not an immediate threat, and move on. For most objects, that's sufficient. For interstellar visitors, it should be sufficient. They're passing through. Once you've confirmed they're leaving, there's no reason to keep watching. Except the absence of updates can feel louder than the updates themselves. When months pass without new orbital calculations, Without refined predictions, without reassuring statements that everything remains on course, silence fills the gap. And human minds are exceptionally good at filling silence with narratives, usually the wrong ones. Online, speculation thrives in the gaps. Message boards and social media become echo chambers for anxiety. If the object was really safe, people reason, wouldn't scientists keep saying so? If the trajectory was really predictable, wouldn't there be continuous updates? The lack of information becomes information. Silence becomes evidence of something being hidden, something alarming, something too dangerous to share publicly. This is unfair to scientists who are usually just busy. Observing time on major telescopes is allocated months in advance. Proposals get reviewed, priorities get set, schedules get locked in. An interstellar object that's already been characterized doesn't rank high on the priority list unless something changes. And if nothing has changed, or if the changes are small and within expected error margins, there's no compelling reason to issue updates. No news is legitimately good news, but institutional caution can look like concealment. When official statements carefully hedge with phrases like current observations suggest and within projected parameters, the hedging gets interpreted as doubt. When updates become less frequent, the silence gets interpreted as evasion. And when someone points out that the last detailed trajectory calculation is now 6 months old, that outdated information becomes the seed of conspiracy. Interstellar objects fall outside many standard pipelines. The Minor Planet Center tracks solar system objects. The International Astronomical Union names comets and asteroids. But interstellar visitors don't fit neatly into existing categories. They're not minor planets. They're not quite comets, even when they exhibit comet-like behavior. They're exceptional, which means they require exceptional handling, which means they sometimes slip through bureaucratic cracks. The result is a strange informational void. Everyone agrees 3i Atlas is interesting. Everyone agrees it should be monitored, but no single organisation owns the responsibility of providing regular public updates. NASA watches it. ESA watches it. Amateur networks track it when they can, but coordinated, transparent, ongoing communication. That's harder to maintain when the object isn't an immediate threat and when institutional priorities pull in multiple directions. And then there's the problem of uncertainty. Science communicates uncertainty through error bars, confidence intervals, probability ranges. But public communication wants certainty. News articles want definitive statements. Readers want to know, is it dangerous or not? The honest answer, most of the time, is probably not, but we can't be completely sure. That honest answer satisfies no one. It reads as evasion to critics and as alarmism to optimists. So scientists err on the side of caution. They issue statements that are technically accurate but emotionally unsatisfying. They emphasize that current models show no threat. They avoid speculating about low probability scenarios. They don't want to cause panic, and they don't want to look foolish if their speculation turns out to be wrong. The silence, in that sense, is protective. It's an attempt to avoid creating problems where none exist. But silence is a narrative vacuum, and vacuums get filled. If official sources won't discuss unlikely scenarios, unofficial sources will. If scientists won't speculate about what happens if the models are wrong, internet commentators will. And because unofficial speculation isn't bound by peer review or professional caution, it tends toward the dramatic. The worst-case scenario gets amplified. The possibility becomes a probability. The probability becomes a certainty. None of this means 3i Atlas is actually dangerous. It doesn't mean the models are wrong. It doesn't mean anyone is hiding information. It just means that in the absence of continuous, clear, reassuring communication, human psychology fills the gap with anxiety. And once that anxiety takes root, it's hard to dislodge. The silence isn't evidence, but it's also not nothing. It's a gap in information, a pause in communication, a space where certainty used to be and now isn't. And as 3i Atlas continues its journey through the outer solar system, that gap widens. The last confirmed trajectory becomes older. The confidence intervals become fuzzier. The question shifts from where is it now to where was it when we last checked? And if it comes back? If decades from now, a new object is detected on an Earth-crossing orbit, and someone runs the calculations backward and realizes it matches 3i Atlas perfectly, the silence we're hearing now will sound very different in retrospect. Not like caution, like a warning no one wanted to give. Part 6. Non-gravitational forces, too small, or misread. Outgassing pushes comets. That's the simple version. Solar radiation heats the surface. Ice sublimates into gas. The gas escapes, and conservation of momentum means the comet gets pushed in the opposite direction. It's rocket propulsion at microscopic scale, continuous and gentle. For most comets, it's a small effect compared to gravity, measurable but not dominant. Except small effects accumulate, and over multiple orbits, those tiny pushes add up to significant trajectory changes. But here's what the simple version leaves out: direction. Not all outgassing is created equal. A comet that vents uniformly from all sides experiences forces that cancel out. The thrust from one hemisphere is balanced by thrust from the opposite hemisphere. Net effect, nearly zero, but comets don't vent uniformly. Solar heating creates a day-night temperature difference. The side facing the sun sublimates more aggressively. The night side, still cold, vents less or not at all. The result is asymmetric thrust, a net force pointing away from the sun. Except even that's an oversimplification. Comet nuclei rotate. As they spin, different parts of the surface face the sun. If the rotation is fast enough, the day-night asymmetry averages out over time. But if the rotation is slow, or if the comet is tidally locked, or if internal heat sources create venting that doesn't depend on solar heating, the thrust becomes persistent in one direction. That's when outgassing stops being a minor perturbation and starts being a significant orbital force. For 3I Atlas, we don't know the rotation state. We know it's an interstellar object, which means it formed around a different star, in conditions we can't observe directly. We know it's moving fast, which suggests it was ejected violently from its home system, or accelerated by close encounters we'll never witness. We know it exhibits some comet-like characteristics based on spectroscopic observations, which implies it contains volatiles. But rotation, surface composition, internal structure, educated guesses at best, and those guesses matter. If 3I Atlas is tumbling chaotically, outgassing probably averages out. If it's rotation locked or spinning slowly, outgassing could produce persistent thrust. If the axis of rotation happens to align with the direction of motion, or perpendicular to it, or at some other specific angle, the thrust vector changes. And the thrust vector determines whether outgassing speeds the object up, slows it down, or deflects it sideways. Now consider what happens near Jupiter. Solar heating decreases with distance from the Sun, but gravitational perturbations can crack surfaces, exposing fresh volatiles. Tidal forces from Jupiter's gravity can flex the object slightly, generating internal heat through friction. If 3I Atlas passes close enough to Jupiter, these tidal effects could trigger outgassing episodes that wouldn't occur otherwise. The venting wouldn't be driven by sunlight. It would be driven by gravitational stress. This is speculation, but it's grounded in observed phenomena. Io, Jupiter's innermost large moon, is the most volcanically active body in the solar system, precisely because Jupiter's tidal forces heat its interior. Enceladus, a moon of Saturn, vents water vapour from cracks in its icy crust driven by tidal flexing. Tidal heating is real, it's well documented, and if it can drive volcanism on moons, it can drive outgassing on a comet-like interstellar object passing close to Jupiter. So now we have two sources of thrust: solar-driven outgassing, which decreases with distance from the Sun but persists as long as surface ice is exposed, and tidal-driven outgassing, which spikes during close approach to Jupiter and then fades as the object moves away. Both are non-gravitational forces. Both are small compared to gravity, but both are cumulative. Here's where the size question becomes critical. How much thrust is too small to matter? For a spacecraft, engineers measure thrust in newtons or pounds force. For a comet, scientists measure it by looking at orbital deviations and working backward to infer the force required to produce them. The numbers are usually tiny, fractions of a newton, less force than you'd use to lift a glass of water, but applied continuously over weeks or months, even a fraction of a newton can shift an orbit by thousands of kilometres. The problem is measurement. We don't measure the thrust directly. We can't. There's no accelerometer on 3I Atlas, no telemetry, no sensors. We observe the object's position, compare it to predictions, and attribute any mismatch to non-gravitational forces. That attribution involves assumptions. If the object is brighter than expected, we assume outgassing. If it's moving slightly faster, we assume thrust is aligned with motion. If it's deflecting sideways, we assume a symmetric venting. But what if the assumptions are wrong? What if the brightness change is due to rotation bringing a reflective surface into view, not outgassing? What if the velocity change is due to measurement error, not real acceleration? What if the deflection is caused by a force we haven't considered at all? The residuals tell us something is happening. They don't tell us what. And then there's the coherence problem. For outgassing to produce a significant trajectory change, the thrust needs to be coherent. It needs to push consistently in roughly the same direction for an extended period. Random venting, chaotic and directionally unstable, produces noise. Coherent venting, persistent and directional, produces signal. We can measure signal. Noise gets lost in observational uncertainty. For most comets, coherence comes from rotation. The comet spins, but the spin axis stays fixed. So outgassing jets keep pointing in consistent directions relative to the comet's orbit. Over time, those jets act like small engines firing repeatedly in the same direction. The effect accumulates. For 3I Atlas, if the rotation is stable and the venting is asymmetric, the same accumulation occurs. Small forces become significant forces. But we don't know if the rotation is stable. We don't know if the venting is asymmetric. We're inferring behavior from indirect observations and trying to fit those inferences into models built for solar system objects. If 3I Atlas behaves differently, if interstellar objects follow rules we haven't discovered yet, the models fail quietly. The predictions drift, and the drift gets attributed to observational noise until it becomes too large to ignore. So are non-gravitational forces on 3I Atlas too small to matter? Or are they just misread, misattributed, misunderstood? The honest answer is we don't know. The observed forces are small, measured in millimeters per second squared. But small doesn't mean irrelevant. In orbital mechanics, especially at high velocities near massive bodies, small forces applied at the right time can bend trajectories in ways that make the difference between flyby and return. Intriguing, not alarming. That's the official line. The forces are interesting, worth studying, but not threatening. Probably, assuming the measurements are accurate, assuming the models are complete, assuming nothing has been missed. Part 7. The orientation anomaly. Spin matters. That's one of those deceptively simple statements that hides enormous complexity. An object tumbling through space doesn't just move along its orbital path, it rotates. And how it rotates affects everything. How it reflects sunlight, how it vents gas, how it responds to gravitational gradients, how it interacts with radiation pressure. Change the spin state and you change the behavior. For most asteroids and comets, rotation is chaotic. Collisions during formation imparted random angular momentum. Gravitational encounters tweaked the spin axis. Outgassing created torques. The result is tumbling, complex rotation that doesn't settle into a stable configuration. Measuring this rotation is difficult. You observe brightness variations as different faces reflect sunlight, fit a model to the light curve, and extract the rotation period. Sometimes you get lucky and the rotation is simple, a single axis with a clean period. Often it's not. For interstellar objects, rotation is even harder to measure. They're faint, they're far away. They move quickly across the sky. Observation windows are short. By the time you've gathered enough data to characterize the light curve, the object is already receding and getting dimmer. Oumuamua is a perfect example. Astronomers observed it for a few weeks, long enough to determine it was elongated and tumbling, but not long enough to fully resolve the spin state. Questions remain. For 3I Atlas, rotation measurements are incomplete. Early observations suggested a period of several hours, consistent with many comets. But the light curve is noisy. There are irregularities that don't fit simple rotation models. Some researchers have suggested precession, where the rotation axis itself wobbles. Others have proposed complex rotation, tumbling around multiple axes simultaneously. Without extended observations, it's impossible to know for certain. But here's why spin state keeps coming up in analyses: gravitational coupling. When an elongated object passes near a massive body like Jupiter, tidal forces interact with the object's shape. If the long axis happens to point toward Jupiter during closest approach, the tidal gradient tries to stretch the object. If the object is rotating such that different orientations face Jupiter at different times, the tidal forces average out. But if the object's rotation is synchronized with its orbital motion, if it's tidally locked even temporarily, the coupling becomes persistent. Tidal locking is common in the solar system. The moon is tidally locked to Earth, always showing the same face. Many moons of Jupiter and Saturn are tidally locked to their planets. The mechanism is friction. Tidal flexing generates heat, dissipates rotational energy, and gradually slows the rotation until it matches the orbital period. For a comet passing Jupiter once, there's not enough time for full tidal locking. But temporary gravitational coupling? That's possible, and if gravitational coupling occurs during the close approach, it affects the trajectory. An elongated object aligned with Jupiter's gravity gradient experiences different forces than a tumbling object. The torques change, the energy transfer changes, the exit velocity and direction change, and because we don't know the exact spin state, we can't fully model the interaction. This isn't conspiracy. This isn't hidden information. This is the fundamental problem of insufficient data. Measuring spin state requires extended observations from multiple angles. For a fast-moving object like 3I Atlas, you don't get multiple angles. You get whatever angle it happens to present during the brief window when it's bright enough to observe. If that angle doesn't reveal the spin clearly, you're left guessing. And then there's the question of statistical rarity versus impossibility. Some researchers have noted that if 3I Atlas were oriented in a specific way during its Jupiter flyby, with its long axis aligned perpendicular to its velocity vector, and its rotation axis aligned with Jupiter's gravitational gradient, the resulting trajectory change would be maximized. That's a very specific configuration. Multiple parameters all need to line up. What are the odds? Hard to say. If rotation is random, the odds are low. One configuration out of hundreds or thousands of possible orientations. But if rotation isn't random, if the object's spin state was influenced by earlier gravitational encounters or by outgassing torques, the configuration might be more likely. And even if the odds are low, low doesn't mean zero. Rare things happen. That's why we call them rare, not impossible. The problem is that rarity feels suspicious. When multiple unlikely things happen in sequence, pattern-seeking minds start connecting dots. 3I Atlas approaches Jupiter at high speed. Its trajectory brings it close enough for significant gravitational interaction. Its spin state, poorly understood, happens to be in a configuration that maximizes the deflection. It exhibits non-gravitational forces at the worst possible time, and the resulting trajectory sends it back toward the inner solar system. Each step individually is plausible. Together, they feel orchestrated. But nature doesn't orchestrate. Nature is indifferent. If the configuration is rare but possible, and if the physics allows it, then it happens without needing a reason beyond chance. The universe is large. Time is long. Rare events occur constantly somewhere, somewhen. The question is, are we witnessing one? Observational limits compound the uncertainty. Ground-based telescopes struggle to resolve details on an object that's hundreds of millions of kilometers away. Space-based telescopes have better resolution but limited observing time. You get snapshots, not continuous monitoring. And from snapshots, you have to infer motion, rotation, surface properties, outgassing activity, everything. It's like trying to understand a car's engine by looking at a few photographs taken from far away. You can make educated guesses, but you're always missing information. And that missing information is where speculation lives. If we knew the exact spin state, we could model the Jupiter encounter precisely. If we knew the surface composition, we could predict outgassing patterns. If we knew the internal structure, we could calculate tidal responses. But we don't know. We infer. We approximate. We model based on assumptions borrowed from other objects that might not apply. So when someone says the orientation of 3I Atlas is anomalous, what they mean is, the available data doesn't cleanly fit the simple models. There are irregularities. There are unexplained features in the light curve. There are residuals in the trajectory. Could these be measurement artifacts? Yes. Could they be evidence of unusual rotation? Also yes. Could they be signs of something we haven't considered? That too. Coincidence versus intent. The distinction matters psychologically but not physically. Physics doesn't care why an object is oriented a certain way. It only cares that it is. If the orientation produces a specific outcome, the outcome occurs regardless of whether the orientation was random chance or deliberate positioning. Humans want to assign meaning to patterns. Physics just follows the math. But the math is unsettling when the patterns keep recurring. And the pattern here is that multiple factors, each individually uncertain, combine in ways that nudge the trajectory in a consistent direction. away from escape, toward return, maybe, possibly, if the models are missing something. Part 8. Could Jupiter be used deliberately? Let's be absolutely clear from the start. This section is speculative. This is a thought experiment. There is no evidence that 3i Atlas is under intelligent control. There is no indication that its trajectory is anything other than the result of natural gravitational and non-gravitational forces. But thought experiments serve a purpose. They explore possibilities, test boundaries, and force us to consider scenarios that might otherwise seem too unlikely to examine. So let's examine. Jupiter is the largest energy reservoir in the solar system after the Sun. Not in terms of radiation or heat, but in terms of gravitational potential. If you want to change your velocity or direction in space, you have two options. Bring fuel and burn it, or find a gravity well and use it. Fuel is expensive. You have to launch it from Earth, carry it with you and burn it efficiently. Gravity wells are free. You just have to aim correctly and let physics do the work. Mission designers at NASA and ESA know this. Every deep space probe launched in the past 40 years has used gravity assist to reach its destination. Voyager, Galileo, Cassini, New Horizons, Juno, all of them used Jupiter at some point. The mass of Jupiter is so enormous that a close flyby can add or subtract kilometers per second of velocity with no fuel expenditure. It's the ultimate force multiplier. Here's the key insight. The closer you approach, the more energy you can exchange. Voyager 1 passed within about 350,000 kilometers of Jupiter's cloud tops. At that distance, Jupiter's gravity bent the spacecraft's path by tens of degrees and increased its velocity by more than 10 kilometers per second. If Voyager had passed even closer, the effect would have been greater. There's a mathematical relationship. Energy transfer scales with proximity. Now imagine an object designed to maximize that transfer. Not a probe with a fixed trajectory, but something that could adjust its approach angle, its timing, its orientation. You wouldn't need much thrust. A few meters per second of delta V applied at the right moment could shift your perihelion by hundreds of kilometers, and those hundreds of kilometers change the gravitational deflection angle, which in turn changes the exit velocity and direction by thousands of kilometers per second over the course of the flyby. This is why gravity assists are so powerful for spacecraft. A tiny engine burn at periapsis gets amplified by Jupiter's gravity into a massive trajectory change. Engineers call it the Oberth effect. Thrust applied when you're moving fast and deep in a gravity well produces more change in orbital energy than the same thrust applied elsewhere. It's not magic, it's conservation of energy combined with the nonlinear geometry of orbital mechanics. So theoretically, could an object use Jupiter deliberately? Could something with minimal propulsion capability execute a powered slingshot designed to redirect itself? From a pure physics standpoint, yes. Absolutely. The math allows it. You'd need precise timing, accurate knowledge of Jupiter's position and mass, and the ability to apply thrust at specific moments during the encounter. But the energy requirements are shockingly low. A few hundred meters per second of delta V, applied strategically, could turn a flyby into a U-turn. Compare this to interplanetary travel. Getting a spacecraft from Earth to Mars requires kilometers per second of delta V. Reaching the outer planets requires even more. But if you're already moving at interstellar speeds and you just want to redirect, the requirements drop. You're not accelerating from rest. You're nudging an existing trajectory. The energy is already there. You're just redistributing it. And Jupiter is uniquely suited for this. Saturn has significant gravity, but it's farther from the Sun and less accessible. Uranus and Neptune are even more distant. Earth and Venus are too small. Mars is tiny. Jupiter sits at the perfect location, close enough to the inner solar system for practical access, massive enough to provide enormous gravitational assist potential. If you were planning an interstellar trajectory and you wanted to use local resources to change course, Jupiter is the obvious choice. But here's the uncomfortable part. This kind of maneuver requires information. You need to know where Jupiter is. You need to know how to time your approach. You need to understand orbital mechanics at a level that suggests either advanced intelligence or extremely sophisticated autonomous systems. Natural objects don't plan. They don't calculate. They don't time their outgassing to coincide with gravitational encounters. Unless. What if the apparent timing is coincidence? What if 3i Atlas is venting gas naturally? driven by solar heating or internal processes, and it just happens to be venting at moments that align with gravitationally significant portions of its trajectory. Unlikely, but not impossible. We've already established that rotation state affects outgassing direction. If the rotation happens to be synchronized, even loosely, with the orbital motion, outgassing becomes semi-coherent, not planned, just fortunate. Or what if the object isn't natural? What if it's a probe from another civilization, designed to survey stellar systems by using gravity assist to maneuver through them? This is peak speculation, but it's worth considering for the thought experiment. A probe wouldn't need to be large. It could be mostly inert, with minimal active systems. It could use solar heating to trigger outgassing from onboard volatiles, using natural processes as its propulsion system. It could time its maneuvers by measuring gravitational gradients and adjusting accordingly. All of this is theoretically possible, with technology humans don't yet possess, but which isn't prohibited by known physics. And if such a probe existed, Jupiter would be its ideal tool. Approaching from interstellar space, it could use the Sun's gravity to decelerate slightly, then use Jupiter to redirect without expending significant fuel. The entire inner solar system becomes accessible with minimal energy cost, and the maneuver would look, to external observers, like a natural gravitational deflection combined with minor non-gravitational forces. Only detailed analysis would reveal that the forces are suspiciously well timed. None of this is evidence, none of this is happening. This is pure speculation, the kind astronomers discuss privately over coffee and dismiss publicly because extraordinary claims require extraordinary evidence and there is none. But the physics is valid. The possibility exists, and that possibility is psychologically unsettling because it shifts the question from could nature do this to could intelligence do this. The answer to both is yes. Nature could produce a lucky alignment of rotation, outgassing and trajectory that results in a Jupiter-assisted U-turn, and intelligence could plan one. Distinguishing between the two from observational data alone? Nearly impossible. You'd need evidence of active guidance systems, detectable propulsion signatures or communications. So far none have been found. So why even discuss this? Because it forces clarity. If we're worried about 3-Eye Atlas, we should be clear about what we're worried about. Are we worried that a natural object through sheer bad luck is on a collision course? Or are we worried that it's not natural? The distinction matters. Natural objects are predictable, even if we don't fully understand them. Artificial objects are not. They can change course. They can respond to circumstances. They can surprise us. But there's a third option. Maybe it doesn't matter. Maybe the outcome is the same regardless of intent. If an object is heading toward Earth, whether it got there by accident or design is philosophically interesting but practically irrelevant. The response is the same. Observe, calculate, prepare. Intent doesn't change physics. A kinetic impact at 60 kilometers per second releases the same energy whether the object is a comet or a probe, except it does matter in one sense. If the object is under control, prediction becomes harder. You can't model what you can't anticipate. And if there's intelligence behind the trajectory, we're not just dealing with orbital mechanics, we're dealing with strategy. That elevates the problem from astrophysics to something else entirely, something we're not remotely prepared for. Part 9. If it comes back, miss, flyby, or impact. Let's say, hypothetically, that every fear discussed so far proves justified. The models are wrong. The trajectory has changed. 3-Eye Atlas is not leaving the solar system. It's returning. Decades from now, or centuries, but returning. What happens next depends entirely on the specifics of the return trajectory, and those specifics span a range from benign to catastrophic. First, the miss. Most return trajectories, even if they bring an object back into the inner solar system, don't result in Earth impacts. Space is vast. Earth is tiny. The orbital plane of Earth is a thin disk. An object returning from interstellar space has to intersect that disk at the exact moment Earth happens to be at the intersection point. The timing requirements are absurdly precise, off by hours, and Earth is hundreds of thousands of kilometers away from the crossing point, off by days, and it's millions. So most likely scenario, 3-Eye Atlas returns, passes through the inner solar system, and misses Earth completely. Maybe it passes close to Mars. Maybe it makes another Jupiter encounter and gets redirected again. Maybe it finally leaves for good. The point is, return doesn't automatically mean danger. It just means the object is back in our neighbourhood. But close encounters matter even without impact. A flyby within a few million kilometres would be scientifically invaluable. Telescopes would have another chance to observe the object up close. Spectroscopy could reveal surface composition. Radar could measure rotation and shape. We'd learn more in a few weeks of close observation than we learned during the entire first pass. And if the object exhibits unusual properties, we'd have time to study them properly. From a public safety standpoint, a close flyby also provides warning. If 3i Atlas passes Earth at, say, lunar distance, about 400,000 kilometres, that's alarming but not immediately threatening. It proves the trajectory can bring the object close. It suggests future encounters might be closer. It gives planetary defence systems a real target to plan against. And it focuses attention in ways that distant speculation never could. Now the darker scenario. What if the return trajectory doesn't miss? What if the geometry aligns, the timing coincides, and 3i Atlas intersects Earth's orbit precisely when Earth is there? Then you have an impact. And at 60 plus kilometers per second, the energy involved is staggering. Kinetic energy scales with velocity squared. An object moving at 60 kilometers per second has 36 times the kinetic energy per kilogram as the same object moving at 10 kilometers per second. Most asteroids that threaten Earth are moving at 15 to 25 kilometers per second at impact. They're already devastating at those speeds. Chicxulub, the asteroid that contributed to the extinction of the dinosaurs, hit at approximately 20 kilometers per second. Its kinetic energy was equivalent to billions of nuclear weapons. Scale that up to 60 kilometers per second. An object the size of a football field, perhaps 200 meters across, would release energy equivalent to thousands of megatons. Not a global extinction event, but a regional catastrophe. If it hit an ocean, the tsunami would devastate coastlines thousands of kilometers away. If it hit land, the immediate destruction would span hundreds of kilometers. The atmospheric shockwave would circle the globe. The debris lofted into the stratosphere would affect climate for years, and we wouldn't be able to stop it. This is the hard truth that planetary defense experts don't like to discuss publicly. Current systems are designed for slower objects. DART, the Double Asteroid Redirection Test, successfully altered the orbit of an asteroid by ramming it at about 6 kilometers per second. That's impressive. But DART relied on having time to reach the target, line up the intercept and execute the impact. For a slow-moving asteroid discovered years in advance, that's feasible. For 3i Atlas, moving at 10 times the speed and potentially arriving with much less warning, DART is useless. You can't intercept something moving that fast with current technology. The closure rate is too high. The launch windows are too narrow, and even if you manage to hit it, the kinetic energy transfer would be insufficient to deflect it meaningfully. Deflection requires changing velocity. To deflect an object off a collision course with Earth, you need to change its velocity by at least tens of meters per second, depending on warning time. The less time you have, the more delta V you need. For an object discovered a decade before impact, a few centimeters per second might suffice. For an object discovered months before impact, you need meters per second. For an object discovered weeks before impact, you're talking kilometers per second of required delta V, and 3i Atlas is massive. Estimates suggest tens of thousands to hundreds of thousands of tons. Changing the velocity of that much mass requires enormous energy. A nuclear explosion near the surface might work if you could get there in time, but the effectiveness depends on standoff distance, surface properties, and whether the explosion vaporizes material asymmetrically enough to produce thrust. It's not impossible, but it's far from guaranteed. So what about atmospheric grazing? If 3i Atlas approaches at a shallow angle, it might skim Earth's upper atmosphere without fully impacting. The drag would heat the object, possibly fragmenting it, but the bulk of the mass might survive and continue into space. This happened with meteors regularly, objects entering the atmosphere at shallow angles, slowing down, heating up but not impacting. Except at 60 kilometers per second, atmospheric grazing becomes atmospheric catastrophe. The object would compress the air ahead of it, creating a shockwave of superheated plasma. The energy deposited into the atmosphere would be equivalent to a massive explosion, even without ground impact. The Chelyabinsk meteor in 2013 entered at about 19 kilometers per second and exploded in the air with energy equivalent to 400 to 500 kilotons. 3i Atlas, moving 3 times faster, would be exponentially worse. And then there's the warning time problem. How much notice would we have? If 3i Atlas returns on a predictable elliptical orbit after its Jupiter encounter, we might track it for years or decades before the collision. That's best case. But if the orbit is chaotic, if close encounters with other planets keep perturbing it, we might not get confident predictions until months before impact, and months is not enough time to mount a meaningful defense. Current detection systems are optimized for objects that are already near Earth. Pan-STARRS, the Catalina Sky Survey, these telescopes scan the sky repeatedly looking for moving objects. They're good at finding asteroids a few months to a few years before potential impacts. But something coming from the outer solar system at high speed? That's harder. The object is faint until it gets close. By the time it's bright enough to track accurately, it's already inbound. So the nightmare scenario is this. 3i Atlas returns. We don't detect it until it's a few months out. Orbital calculations confirm an Earth impact trajectory. We have no way to deflect it. Evacuation is pointless because we don't know exactly where it will hit until days before impact. All we can do is watch and wait and hope we've miscalculated. No impact trajectory is currently predicted. Let me repeat that. No impact trajectory is currently predicted. This entire section is hypothetical, but hypotheticals prepare us emotionally. They force us to confront possibilities we'd rather ignore. Because if the models are wrong, if the assumptions break down, if 3i Atlas really is coming back, we need to understand what that means before it happens, not after. Part 10. Planetary Defense. Built for the wrong enemy. DART worked. On September 26, 2022, NASA's Double Asteroid Redirection Test spacecraft deliberately crashed into Dimorphos, a small moon orbiting the asteroid Didymos. The impact changed Dimorphos's orbital period by 33 minutes. Mission success. Proof of concept. Humanity demonstrated that we can deflect an asteroid if we see it coming, and we have time to prepare. Except DART was designed for a very specific type of threat. A small asteroid, a few hundred meters across, discovered years or decades in advance, moving at typical near-Earth asteroid speeds of 15 to 25 kilometers per second. Under those conditions, a kinetic impactor works beautifully. You don't need to destroy the asteroid, you just need to nudge it slightly. A few centimeters per second of velocity change, applied years before a predicted impact, shifts the asteroid's orbit enough to turn a collision into a miss. But those conditions are narrow. Change any parameter significantly, and the approach breaks down. Make the asteroid faster, and the kinetic energy of the impact becomes insufficient to produce meaningful deflection. Make the asteroid larger, and you need more energy. Reduce the warning time, and the required velocity change increases beyond what a single kinetic impact can deliver. DART is a solution to a specific problem. It's not a universal solution. 3i Atlas breaks every assumption DART was built on. It's fast, 60 plus kilometers per second, several times faster than any near-Earth asteroid. It's potentially massive. Size estimates vary, but even conservative numbers suggest tens of thousands of tons, and it's unpredictable. If the trajectory is being influenced by non-gravitational forces we don't fully understand, we can't confidently predict when or where a collision might occur. Speed dominates the problem. Kinetic energy, as mentioned before, scales with velocity squared. A collision at 60 kilometers per second releases 36 times more energy per kilogram than a collision at 10 kilometers per second. But from a deflection standpoint, speed creates a different problem. Intercepting a fast-moving object is harder. The closure rate is enormous. Launch windows are narrow. Trajectory corrections have to be precise. Think about intercepting a bullet. Possible, in theory, if you know exactly where the bullet will be and when. You put something in its path at the right moment and they collide. But if the bullet is moving at hypersonic speeds and you don't know its exact trajectory until seconds before impact, interception becomes nearly impossible. You're trying to hit a moving target with another moving object, and the timing requirements are measured in fractions of a second. For 3i Atlas, the timing problem is worse because we can't launch interceptors on demand. Rockets take time to prepare, orbits have to be calculated, transfer trajectories have to be optimized. Even in a crisis, launching a mission to intercept an object beyond Mars would take months to years, and if the object is already in the inner solar system, there's no time to reach it before it reaches Earth. So what about nukes? Hollywood loves nuclear solutions. Drill into the asteroid, plant a bomb, blow it up. Problem solved, except blowing up an asteroid doesn't eliminate the threat. it fragments it. Now, instead of one large object hitting Earth, you have dozens or hundreds of smaller objects. Some burn up in the atmosphere, some still impact. The total kinetic energy is unchanged. You've turned a rifle bullet into a shotgun blast. Nuclear deflection is more nuanced. The idea isn't to destroy the object, but to vaporize material on one side, creating an asymmetric jet that acts like a rocket engine. The expanding vapor pushes the asteroid, changing its velocity. This could work, in theory, if you can get close enough, if the surface composition allows efficient vaporization, and if you have enough warning time for the velocity change to matter. But 3I Atlas is moving so fast that nuclear deflection becomes questionable. The velocity change needs to be larger to compensate for shorter warning times. The standoff distance for the explosion has to be carefully calculated. Too close, and you fragment the object. Too far, and the energy dissipates without producing meaningful thrust. And you'd need to launch the nuclear device, rendezvous with the object, position it correctly, and detonate it, all within a narrow time window. And then there's the problem of detection and tracking. Planetary defense assumes we see the threat coming. Current surveys are good at finding near-Earth asteroids, objects that orbit the Sun and periodically come close to Earth. We've catalogued most of the large ones, the ones that could cause global devastation. We're working on cataloguing the medium-sized ones, the city killers. But interstellar objects? We've only confirmed 3. They're dark, fast, and hard to spot until they're already close. If 3I Atlas returns on an unpredictable trajectory, we might not see it until it's already approaching the inner solar system. At that point, the warning time is measured in months, maybe weeks. That's not enough time to design, build, launch, and execute an intercept mission. It's barely enough time to evacuate populations if we know where it's going to hit. And orbital uncertainties mean we might not know the impact location until days before the event. So what can we do? Honestly, not much. Current systems are optimized for known threats, slow threats, threats we discover years in advance. For something like 3I Atlas, if it's truly coming back, we'd be limited to observation and prediction. Track it as best we can, calculate the impact probability, refine the trajectory as more data comes in, and prepare for the consequences rather than trying to prevent them. This is uncomfortable but honest. Planetary defense is in its infancy. DART was a first step, a proof that deflection is possible. But it's a first step in a very long journey. Building systems that can handle fast, massive, unpredictable objects will take decades and enormous resources. We'd need better detection networks, faster response capabilities, more powerful propulsion systems, and a willingness to invest in threats that might never materialize. And that's the political problem. Funding planetary defense is hard when the threat is abstract. Asteroids don't respect election cycles. The risk is spread over centuries. No politician wants to spend billions on a problem that might not occur in their lifetime. So we do the minimum, we track what we can, we test technologies slowly, and we hope that if something really dangerous appears, we'll have time to respond. But hope is not a strategy. And if 3I Atlas is the warning shot, the object that reveals how unprepared we are, then the question becomes, do we learn the lesson in time? Or do we wait until it's too late to matter? Part 11. The Interstellar Object Boom. 2017. Oumuamua, the first confirmed interstellar object ever detected passing through our solar system. Astronomers celebrated. This was historic. A visitor from another star, proof that stellar systems exchange material across the galaxy. The object was strange, elongated, tumbling, exhibiting acceleration that didn't fit pure gravitational models, but it was there. It was real. 2019. 2I Borisov, the second interstellar object. This one was easier to classify, clearly a comet based on spectroscopic observations. It behaved more like expected, outgassing and displaying a coma. Less mysterious than Oumuamua, but still extraordinary. 2 interstellar visitors in 2 years. The floodgates seem to open. 2023, 3I Atlas. And now the question is, how many more are coming? Are we witnessing the start of an interstellar object boom, a sudden influx of visitors from beyond our solar system? Or are we just getting better at detecting them? The answer is mostly the latter. Interstellar objects have always been passing through. They didn't suddenly start showing up in 2017. What changed is our ability to see them. Advances in telescope technology, better survey programs, more sensitive detectors, improved data processing. Pan-STARRS, the Panoramic Survey Telescope and Rapid Response System, came online in the early 2010s. The Catalina Sky Survey expanded its operations. ATLAS, the Asteroid Terrestrial Impact Last Alert System, began scanning the sky repeatedly for transient objects. These surveys weren't designed to find interstellar objects specifically. They were designed to find near-Earth asteroids, the ones that pose impact threats. But their methods work for anything that moves, and interstellar objects move fast. That motion is what makes them detectable. Over the course of a few nights, an interstellar object shifts position dramatically against the background stars. Automated systems flag it. Astronomers follow up, and if the trajectory shows hyperbolic excess velocity, it gets classified as interstellar. But there's a selection bias. We're most likely to detect interstellar objects that pass close to the Sun and Earth. Objects that pass through the outer solar system beyond Jupiter are too faint to see. Objects that approach from directions the surveys don't cover get missed. And objects that are small or dark or both are invisible until they're extremely close, at which point they're already leaving. So the 3 confirmed interstellar objects we've detected are just the tip of the distribution. For every one we see, dozens or hundreds pass through undetected. Population estimates based on detection rates suggest that at any given time, there might be thousands of interstellar objects in the solar system. Most are small, most are far from the Sun, most will never come close enough to Earth for observation. But that's a lot of traffic. Thousands of objects from other stellar systems drifting through our neighbourhood, each carrying information about the conditions in distant planetary systems, the violence of stellar evolution, the mechanisms of ejection and capture. We're only beginning to understand this population because we've only just started detecting them, and detection rates are going to increase. The Vera C. Rubin Observatory, scheduled to begin operations soon, will revolutionise sky surveys. It will detect fainter objects, cover more of the sky, and revisit areas more frequently than any previous survey. Estimates suggest it might find dozens of interstellar objects per year, not because the population is increasing, but because our ability to see them is improving. More detections mean better statistics. Right now, we're trying to understand interstellar objects based on 3 examples. That's like trying to understand Earth's ecosystem by looking at 3 animals. The sample size is too small. Once we have dozens or hundreds of detections, we can start characterizing the population. What are the typical sizes, typical velocities, typical compositions? Are most of them asteroid-like or comet-like? Do they cluster in certain trajectories or approach from all directions equally? These questions matter for planetary defense. If interstellar objects are common, if they're routinely passing through the inner solar system, then the threat probability increases, not dramatically. Space is still vast and Earth is still tiny. But more objects means more chances for a close encounter, and eventually more chances for an impact. And there's another implication. If interstellar objects are abundant, then stellar systems are leaking material into the galaxy constantly. Planets form around stars, collisions and gravitational interactions eject debris, and that debris wanders. Some of it gets captured by other stellar systems. Some of it drifts indefinitely. The galaxy becomes a mixing reservoir, homogenizing material over billions of years. This has consequences for astrobiology. If life ever arose on a planet in another stellar system, and if that planet was destroyed or sterilized, fragments might escape as interstellar objects. Microbes could survive in the interior of a comet nucleus, protected from radiation and cold. Those microbes could drift through space for millions of years and eventually land on another planet, seeding life elsewhere. Panspermia, not just within a single stellar system, but across the galaxy. Speculative, sure, but no longer absurd. If interstellar objects are common, if they carry organic material, if impacts between them and planets are inevitable over geological time, then life might be a galactic phenomenon rather than isolated accidents. And every interstellar object we detect is a potential data point in that larger story. But in the short term, the boom in detections means more uncertainty, more objects to track, more trajectories to calculate, more potential threats to assess. Planetary defense systems were designed assuming the threat comes from solar system objects with well-characterized orbits. Interstellar objects break that assumption. They appear with little warning, move unpredictably, and disappear before we can study them thoroughly. And if one of them is on a return trajectory, if 3i Atlas or some future visitor executes a gravitational maneuver that sends it back toward Earth, Then we need to understand these objects better, not just as astronomical curiosities, but as potential hazards, because the boom in detections is also a boom in uncertainty. More objects means more chances for something to go wrong. Part 12. AI is now designing orbits faster than humans. Trajectory prediction used to be straightforward. You observe an object's position at multiple times, fit an orbit to those observations, and propagate forward. Kepler's laws, Newton's equations, maybe some perturbations from other planets. Computers made the calculations faster, but the process remained conceptually simple. Input observations, output trajectory. Done. Except for objects like 3i Atlas, where non-gravitational forces matter, where observational uncertainties are large, where the trajectory depends on parameters we don't directly measure, the process becomes complex. You have to fit models with multiple free parameters. Mass, rotation, outgassing rate, surface albedo, even the object's shape. Each parameter affects the trajectory slightly. Finding the combination of parameters that best fits all the observations requires searching through a multidimensional space. Humans can do this. It's tedious. You run a simulation with one set of parameters, compare the predicted positions to the observations, adjust the parameters, run again. Iterate until the fit converges. The process works, but it takes time, days or weeks to fully characterize a single object's trajectory, and if new observations come in, you start over. Enter machine learning. Over the past few years, researchers have started using neural networks to predict trajectories. Feed the network a training set of simulated orbits. Let it learn the relationships between observations and orbital elements, and then apply it to real data. The network can test thousands of parameter combinations simultaneously, finding optimal fits faster than traditional methods, and it works. AI-driven trajectory predictions are now competitive with, or better than human-generated ones for many objects. The algorithms are fast, scaling effortlessly to large datasets. They're also good at pattern recognition, finding correlations humans might miss. For asteroid surveys that track thousands of objects simultaneously, AI is becoming indispensable. But there's a problem. Black boxes. Neural networks don't explain their reasoning. They don't show their work. You input data, you get predictions, but the intermediate steps are opaque. A human analyst can look at an orbit fit and understand why certain parameters were chosen, which observations were weighted more heavily, where the uncertainties come from. An AI just outputs numbers. This creates verification challenges. How do you know the AI is right? How do you check its work? With traditional methods, you repeat the calculation independently. With AI, you either trust the output or you train a second AI and see if it agrees. Neither option is satisfying, and then there's the risk of overfitting. Machine learning models can become too specialized, learning patterns specific to the training data that don't generalize to new cases. For trajectory prediction, this means the AI might work beautifully on simulated orbits, but fail subtly on real objects that exhibit behaviors outside the training distribution. Interstellar objects are perfect examples. There are only 3 confirmed cases, so training sets have to rely on simulations, and simulations are only as good as the physics we put into them. If the simulations assume certain ranges of outgassing rates, and the real object exceeds those ranges, the AI might produce confident predictions that are completely wrong. And because the AI doesn't explain its reasoning, the error might not be obvious until the object deviates significantly from the predicted path. Speed is not certainty. This is the crucial distinction. AI can generate predictions faster than humans, but faster predictions aren't necessarily more accurate. They're just faster. And in a field where accuracy matters more than speed, where a single misprediction could mean missing an impact warning, relying on opaque algorithms is uncomfortable. Scientists are aware of this. AI is used as a tool, not as a replacement for human judgment. Predictions get cross-checked, anomalies get flagged for manual review. The hope is that AI will catch things humans miss, while humans catch things AI gets wrong. But as the number of tracked objects increases, as survey systems become more automated, the balance shifts. Humans can't review every trajectory manually. At some point we have to trust the machines. And trust is the real issue. Not technical trust, the kind you establish through validation and testing. Psychological trust. The willingness to accept that an algorithm you don't fully understand is making decisions that affect planetary safety. Most people are comfortable with this for mundane applications. Your phone's autocorrect uses AI. Your streaming service's recommendations use AI. But trajectory predictions for potentially hazardous objects? That's different, especially when the AI's predictions conflict with human intuition. If an experienced astronomer looks at an orbit and thinks it's safe, but the AI flags it as risky, who do you believe? Conversely, if the human is worried but the AI says everything is fine, do you relax? The epistemology becomes tangled. Authority shifts from expertise to algorithms, and algorithms can't be questioned in the same way humans can. For 3i Atlas, AI has been used to refine trajectory predictions. The residuals, the deviations between observed and predicted positions, get fed into neural networks that try to infer the non-gravitational forces. The networks output best-fit parameters for outgassing rates, rotation states, surface properties, and those parameters feed back into trajectory models, producing updated predictions. But those predictions are probabilistic. The AI doesn't say the object will be at a specific position at a specific time. It says there's a probability distribution of possible positions, with uncertainties that grow over time. And interpreting those distributions requires human judgment. Is a 1% chance of Earth intersection in 50 years alarming or negligible? Is a 10% chance in 100 years? The AI can't answer. It just provides numbers. So we're in a transitional period. AI is powerful, but not omniscient. It's fast, but not infallible. It's useful, but not sufficient. And as we rely on it more, we need to remain aware of its limitations. Because if AI predicts 3i Atlas is safe and it's wrong, the consequences are severe. And if AI predicts danger where none exists, we waste resources and credibility. The balance is delicate. Use the tools, trust them cautiously, verify constantly, and never forget that the map is not the territory, that predictions are models, and models are simplifications of reality that sometimes miss the details that matter most. Part 13. Solar activity is complicating everything. The sun is not constant. It radiates energy, yes, but that radiation varies. Solar flares, coronal mass ejections, changes in the solar wind, fluctuations in the magnetic field. All of this affects the space environment around Earth and throughout the solar system. And all of it complicates trajectory predictions for small objects. Solar radiation pressure is a force. Photons carry momentum. When they hit an object, they transfer that momentum, pushing it. For large objects like planets, this force is negligible. For small objects like dust grains or spacecraft with large solar panels, it's significant. Comets and asteroids fall somewhere in between. The effect depends on size, mass, and surface area. For a typical comet nucleus, maybe a few kilometers across, solar radiation pressure contributes a tiny acceleration, measured in micrometers per second squared. But over months or years, that acceleration accumulates. The object's velocity changes by meters or tens of meters per second. The trajectory shifts. Predictions that don't account for radiation pressure drift, except the sun's output isn't constant. During solar maximum periods of peak activity, the sun is brighter and more variable. Solar flares can temporarily increase radiation intensity. Coronal mass ejections can alter the solar wind, changing how particles interact with objects in space. These variations affect radiation pressure, making it time-dependent rather than constant, and we're currently in a solar maximum period. The sun's 11-year cycle peaked recently, meaning solar activity is elevated. More flares, more variability, more unpredictability. For objects like 3i Atlas, moving through the outer solar system where solar radiation is already weak, these variations might seem insignificant. But small changes in acceleration over long timescales produce large changes in position. Heliophysics, the study of the sun's influence on the solar system, is still developing. We've learned a lot from spacecraft missions that monitor the sun, from solar probes that dive close to the surface, from Earth-orbiting satellites that measure radiation and particle fluxes. But predicting solar activity remains challenging. We can forecast broad trends, periods of higher or lower activity, but not specific events. Solar flares are notoriously unpredictable, occurring with little warning. This creates a problem for long-term trajectory predictions. If you're trying to predict where 3i Atlas will be in 20 years, you need to account for cumulative effects of solar radiation pressure over that entire period. But if solar activity varies unpredictably, your predictions have to include uncertainties that grow larger the further into the future you project. And there's coupling. Solar radiation pressure interacts with outgassing. When a comet is heated by sunlight, it vents gas. That venting creates thrust. But the heating also depends on how much sunlight hits the surface, which depends on solar output. More radiation means more heating, which means more outgassing, which means more thrust. The forces compound. Now consider that 3i Atlas might have a rotation axis that's not aligned with its orbital plane. Different parts of the surface get heated at different times. Outgassing becomes directionally variable, sometimes pushing the object forward, sometimes sideways depending on which hemisphere is facing the sun. And if solar activity is fluctuating, the heating pattern changes, making the outgassing even less predictable. These are known interactions, but they're hard to model precisely. The coupling between radiation, heating and outgassing is nonlinear. Small changes in one parameter can produce disproportionate changes in outcomes. And when you're dealing with an object billions of kilometers from the sun, where measurements are already difficult, the uncertainties multiply. Recent research has highlighted how much we don't know. Studies of Jupiter family comets, objects that have been observed for decades, show persistent trajectory anomalies that aren't fully explained by current models. The anomalies are small, fractions of a percent, but they're real. Something is missing from the physics. It might be solar activity, it might be complex surface processes, it might be internal structure variations. We don't know. And if we don't fully understand objects we've studied for years, how confident can we be in predictions for an object we've observed for months? This isn't alarmism, this is scientific humility. The universe is complicated. Our models are approximations. They work well enough most of the time, but edge cases expose limitations, and interstellar objects, by definition, are edge cases. For 3i Atlas, solar activity adds one more layer of uncertainty. As it moves through the outer solar system, its trajectory is influenced by subtle forces we can't measure directly. Solar radiation pressure fluctuates. Outgassing responds to heating patterns we can't observe. The cumulative effect over years or decades could shift the object's path by thousands or millions of kilometers, and those shifts might be the difference between a trajectory that brings it back toward Earth and one that doesn't. So when orbital predictions come with large uncertainty ranges, this is part of the reason. Not because scientists are bad at math. Because the inputs to the math are inherently uncertain. Solar activity is one factor among many, but it's one we can't ignore. And as we project further into the future, as the accumulation of small uncertainties grows, the predictions become less reliable. The sun complicates everything, not by being malicious, but by being itself. Variable, powerful, unpredictable. A driver of conditions throughout the solar system, affecting everything that moves. And for objects like 3i Atlas, that influence could be the difference between a benign trajectory and one that demands attention. Part 14, when small forces win. Chaos. In mathematics and physics, chaos has a specific meaning. It doesn't mean randomness, it means sensitive dependence on initial conditions. A system where tiny differences in starting parameters produce drastically different outcomes over time. The classic example is weather. A butterfly flaps its wings in Brazil, and weeks later, a hurricane forms in the Atlantic. Not because the butterfly caused the hurricane, but because weather is chaotic and small perturbations amplify. Orbital mechanics can be chaotic too. For most objects in stable orbits, chaos doesn't matter. Earth orbits the Sun predictably. We can calculate its position centuries into the future with high confidence. Same for the other planets. The orbits are regular, periodic, not chaotic. But add a third body, introduce close encounters, include non-gravitational forces, and chaos emerges. Asteroids in certain orbital regions experience this. The Kirkwood gaps in the asteroid belt, zones where asteroids are conspicuously absent, exist because objects in those orbits undergo chaotic interactions with Jupiter. Over millions of years, the chaos ejects them. Comets, especially long-period comets from the Oort cloud, exhibit chaotic behavior because their orbits bring them close to planets, where gravitational perturbations dominate. For 3i Atlas, approaching Jupiter at high speed, chaos is relevant. The trajectory is sensitive to initial conditions, a slightly different approach angle, a fractionally different velocity, and the exit trajectory changes significantly. This sensitivity means predictions have limited horizons. You can't confidently predict where the object will be in 1,000 years because small errors in current measurements compound exponentially. And it's not just gravitational chaos. Non-gravitational forces introduce additional sensitivity. If outgassing produces thrust, the magnitude and direction of that thrust depend on rotation state, surface properties, solar heating, all of which have their own uncertainties. Stack uncertainties together, propagate them forward in time, and the error bars grow. Eventually they grow so large that the predictions become meaningless. This is a fundamental limit, not a failure of models. Even perfect equations with perfect data have prediction horizons in chaotic systems. Beyond that horizon, you're guessing. The physics is deterministic, meaning if you knew everything perfectly, you could predict everything perfectly. But you don't. You can't. Measurement errors, however small, destroy long-term predictability. Recent findings in physics have reinforced this. Chaos appears in unexpected places. Three-body problems, once thought to be solvable with enough computation, turn out to have chaotic solutions that resist analytical approaches. Gravitational systems with multiple interacting bodies, like planetary systems, can be chaotic over long time scales, even when they appear stable in the short term. The implication for planetary defense is sobering. We can predict near-term threats reasonably well, decades, maybe a century. But beyond that, predictions lose reliability. An object that's calculated to miss Earth by a wide margin in 200 years might hit because of accumulated errors in our understanding of its trajectory. Conversely, an object flagged as potentially hazardous might be harmless once we account for forces we initially missed. Newton's laws still work. This is important to emphasize. Chaos doesn't mean physics breaks down. It means outcomes are sensitive to details. The equations are deterministic and accurate, but garbage in, garbage out. If your initial measurements have errors, those errors amplify through chaos. For 3i Atlas, every measurement has errors. Position measurements are uncertain by hundreds or thousands of kilometers. Velocity measurements have errors of meters per second. Mass estimates are rough. Rotation state is poorly constrained. Each of these uncertainties feeds into trajectory predictions, widening the cone of possible future positions, and the uncertainties grow asymmetrically. Predictions near perihelion, where gravitational acceleration is strongest, are more sensitive than predictions in the outer solar system. Predictions involving close encounters with planets are exponentially more sensitive than predictions for open space trajectories. This means the most critical part of 3i Atlas's trajectory, its Jupiter flyby, is also the least predictable in the long term. This isn't comfortable. We want certainty. We want confident statements that the object is safe or dangerous. But chaos doesn't allow that. It forces probabilistic thinking. Instead of the object will be at position X at time t, we have to say the object has a probability distribution of positions centered near X, with uncertainties that grow over time. And at some point, the distribution becomes so broad that it encompasses both safe and dangerous outcomes. At that point, we're not predicting, we're bracketing possibilities. And the only way to narrow those possibilities is more data, better observations, refined measurements, continuous tracking. But tracking has limits. Objects fade. Telescopes have finite sensitivity. At some distance, 3i Atlas becomes too faint to track accurately, and once we lose tracking, predictions freeze at their last known state. The object keeps moving, forces keep acting on it, the trajectory keeps evolving, but we don't see it. And when we see it again, if we see it again, the position might be far from where prediction suggested. This is the essence of when small forces win. Large forces, like gravity from the sun and planets, dominate trajectories in obvious ways. But small forces like radiation pressure and outgassing operate quietly, accumulated over time, shifting trajectories in ways that only become apparent much later. And in chaotic systems, those small shifts can be the difference between safety and catastrophe. So the question is, are we prepared for this uncertainty? Are we comfortable making decisions based on probabilistic predictions, with error bars that span millions of kilometers? Are we willing to invest resources in monitoring objects that might be harmless, just to be sure? Or do we accept risk as inevitable, gambling that most uncertainties will resolve in our favour? The answer varies. Institutions tend toward caution. Individual researchers push boundaries. The public wants definitive reassurance. and reality remains indifferent, governed by equations that are both perfectly precise and utterly unpredictable beyond certain horizons. Part 15. The question we're avoiding. Let's step back, all the way back. We've discussed trajectories, models, forces, uncertainties, defences, predictions. We've explored scenarios, weighed probabilities, examined assumptions. But underneath all of this analysis is a question we've been dancing around. A question that's uncomfortable because it shifts the conversation from science to philosophy, from facts to fears. Are we certain 3i Atlas is leaving? Not probably leaving, not likely leaving, certain. The kind of certainty that lets you stop tracking, stop worrying, stop preparing. The kind of certainty that makes this entire discussion unnecessary. And the honest answer is no. We're confident based on current models, current data, current understanding. But confidence is not certainty. Models are approximations. Data has errors. Understanding is incomplete. There's a gap between what we predict and what nature will do. And in that gap, surprises live. This is not the same as fear. Fear is emotional, often irrational, driven by worst-case thinking. What we're discussing is epistemic humility, the recognition that knowledge has limits. Science is spectacularly successful at explaining the universe, but it's never complete. There's always another layer of complexity, another parameter we didn't measure, another interaction we didn't model. For most practical purposes, this doesn't matter. We can land spacecraft on Mars without knowing every detail of orbital mechanics. We can predict eclipses centuries in advance despite imperfect knowledge of the Moon's orbit. We're good enough. But good enough for routine operations isn't the same as good enough for existential threats. When the stakes are planetary, when the consequences are irreversible, good enough feels inadequate. So we're left with a tension. Science demands we go where the data leads. But the data, incomplete and uncertain, leads to conclusions hedged with caveats. 3i Atlas is probably leaving. Its trajectory is most likely hyperbolic. Current models suggest no return. These are accurate statements. They're also not absolutes, and humans don't handle probabilistic thinking well. We want binaries, safe or dangerous, known or unknown, leaving or returning. The middle ground, the space of partial knowledge and competing uncertainties, makes us uncomfortable. It feels like indecision, like scientists not doing their job, but it's not. It's honesty. It's acknowledging that some questions don't have clean answers yet. The temptation is to pattern seek, to connect dots, to find meaning in coincidence. 3i Atlas approaches Jupiter. Trajectory shifts slightly. Non-gravitational forces appear. Rotation state is ambiguous. These facts, individually mundane, feel significant together. They form a pattern that suggests something deliberate, something planned. But patterns can be illusory. The human brain evolved to find patterns even where none exist because missing a real pattern was more dangerous than seeing a fake one. So we ask, is the pattern real, or are we imposing narrative onto random events? The difference matters, but distinguishing between them from limited data is nearly impossible. You'd need more observations, more time, more certainty than we have. And by the time you have that certainty, the question might be moot. This is the heart of the problem. Planetary defense requires acting on incomplete information. Waiting for certainty means waiting until it's too late. But acting without certainty means risking resources, credibility, and public trust on threats that might not materialize. The balance is agonizing, and it's compounded by institutional dynamics. Space agencies are conservative, understandably. Making bold claims without evidence damages reputations. Issuing warnings that prove false creates boy-who-cried-wolf scenarios, so the tendency is to wait, to gather more data, to refine models until confidence is high. But waiting has costs too, measured in lost preparation time. For 3i Atlas, we're in the waiting phase. The object is distant, faint, moving away. There's no immediate threat, no imminent danger. The prudent approach is to continue observations when possible, update models as data improves, and re-evaluate if something changes. This is sensible. It's also frustrating for anyone who wants answers now. Because the question remains, what if the assumptions are wrong? What if Jupiter, that massive amplifier of gravitational consequences, has done something we didn't predict? What if 3i Atlas, guided by forces natural or otherwise, is not leaving but looping back? What if the decades or centuries between now and then are not safety buffers but countdown timers? We don't know. That's the answer. We don't know with certainty, and admitting that feels like failure, like science falling short. But it's not. It's science being honest about its limits. It's recognizing that the universe is under no obligation to be comprehensible on our timelines, with our tools at our convenience. Jupiter doesn't choose sides. This is the final, essential truth. Jupiter is a planet, not an agent. Its gravity bends space-time according to equations that don't care about human outcomes. If those equations redirect 3i Atlas toward Earth, it's not an attack, it's geometry. If they deflect it safely away, it's not protection, it's geometry. The universe is indifferent. But indifference doesn't mean inconsequence. A hurricane is indifferent to the cities it destroys. An earthquake is indifferent to the lives it ends. Indifference and danger coexist, and Jupiter's indifference is backed by gravitational power that dwarfs anything we can muster. It shapes trajectories across the solar system, including ours, including anything that comes close. So when we look at 3i Atlas, we're not just looking at an object, we're looking at our relationship with the cosmos. We're confronting the reality that we're small, vulnerable, and reliant on forces beyond our control. Jupiter doesn't protect Earth. Jupiter amplifies consequences, whatever they are. If we're lucky, those consequences favour us. If we're not, they don't. And luck is not a plan. Luck is what you call an outcome you didn't earn, didn't predict, didn't deserve. We can do better. We can observe more carefully, model more accurately, prepare more thoroughly. We can reduce the role of luck by increasing the role of knowledge. But we can't eliminate uncertainty entirely. The universe is too complex, our tools are too limited, time is too short. 3i Atlas might be leaving forever. It probably is. But probably is not certainly. And in the gap between those words, between confidence and certainty, we find the space where vigilance lives, where humility meets curiosity, where science acknowledges what it doesn't know and keeps asking questions anyway. Jupiter doesn't choose sides, it only amplifies consequences, and right now, we don't know which consequences it's amplifying.